Team, I'm just going to use the LISP environment to explore the noise that a switched capacitor makes. Now, whenever we ask this question, we begin with the well-known assumption that the noise of a capacitor is kT upon C. kT upon C. And I have a rule of thumb in my head, which is that 1 picofarad capacitor makes 64 microvolts of noise every time it takes a sample. So this is the LISP environment I use to do engineering. This is from Allegro, Franz, a company called Franz out of California. And I've extended the LISP environment so it understands lots of things to do with engineering. So I'm going to start by just showing you what I mean by that 64 microvolts per picofarad, and we can do it right here. Look, we'll just rip this out of here, this expression out of here. This is the Boltzmann's constant, this is the ambient temperature, this is absolute zero. So kT over C, kT divided by whatever capacitor we have, square root of it. Let's just make that capacitor 1 picofarad, and the answer is 65.23 microvolts. So one of the things you can see is that I've taught LISP how to read and print engineering numbers. Just makes it a lot easier for us. So 1 picofarad, every time it takes a sample, it will make 65 microvolts of error, kT over C. Another thing I've taught this LISP environment is to know what I mean when I do that. 1 shifted left 15 is 32.77. So now let's have a look how we can really come to understand how kT over C noise affects an A to D converter, and it's quite surprisingly interesting. So look what I am going to do. I'm going to make a random Gaussian generator which has a correlation coefficient of 0, a mean value of 0, and a standard deviation equal to the square root of that expression. So let's just make that again over here on the left so that we can understand what's going on. Here in the LISP listener, let me just create that random Gauss thing with 1 picofarad capacitor. Now we have something LISP calls a closure. Every time we call that thing, let's just grabbed it. If a function call that thing, then it will give us a random number, minus 16 microvolts, minus 28 microvolts, minus 81 microvolts. Those numbers have the correct standard deviation. Let's just have a quick hack. Loop, repeat 10,000 times. Again, just show off the numbers. Loop, repeat 10,000 times, collect, function call that thing. There it is. Plot that thing. There it is. What are the statistics of that thing? Math, distribution, simple distribution. There we go. There is that generator. Mean 772 nanovolts, standard deviation 65.66. So that random Gauss guy is cranking out noise, which has the distribution that we're looking for. Okay, back to this guy. Make that random Gauss generator. He makes the same error that the capacitor makes every time. We're going to run for a prime number of cycles. We're going to run for a prime number of cycles in a power of 2 number of samples. You know why that is, right? That's because the standard unmodified Fourier transform works perfectly when there are a prime number of cycles in a power of 2 number of samples. We'll get to that in a minute. The phase factor is just 2 pi number of cycles times Tmax. Tmax is whatever that is. We're running here at 100 megahertz, and that's just the phase factor. That means that's just the thing that appears there. So for time from naught by 1 over the sample, as the input equals sine times the phase factor, as the output equals add to that input a call to a random Gauss generator, collect those guys into Y, finally plot Y sample. We get it, right? That's what's going on. I know it's Lisp, but never mind. Lisp is hard for many people to read, but it's a beautiful and powerful language. So we'll run that function we just created, and there we go. That's what we get. So we generated a sine wave. There's 97 cycles of that sine wave in this window. So when I ask for the FFT of this thing, discrete Fourier transform rectangular, it will be mathematically perfect. Bang, there it is. Right. Now, one of the things that we want to understand is there we've got a sine wave with sampling noise on it, and look, that's the sampling noise that's going on in the background there. I'm going to get rid of that point. There's a cute little way of doing that. I just move it off the screen and say clip everything to what's on the screen. There we go. Now we've got just the noise without the sine wave in it. And now we're going to ask the tool to RMS sum the FFT spectral noise. Bang. That's that graph there. Now I'm going to get rid of that guy, and I'm going to move that axis over to the left. What just happened? This is a graph of the RMS sum of the noise that was in that FFT. Look where it ended up here. It ended up at, look down here, it ended up at 65.39 microvolts. That's what we are taught if we look on the web. We're told that the KT over C noise occupies the Nyquist range. And look at that, that simulation does. There's the 65.39 microvolts, that's the per sample voltage noise of a 1 picofarad capacitor. And there it is at the maximum frequency, the Nyquist frequency that this FFT found for us. That's very encouraging so far, right? I want to know what the noise per square root hertz is. So I'm going to tell this axis to change. I'm going to tell this axis go to the square root, and it does. And then I'm expecting to see that it's linear. So I'll tell that axis to go linear. Whoa, there we go. Right, so I told that axis to take the square root, and then I put it on a linear axis, and it's a constant increase per square root. So now I'm going to ask, what is the derivative of that thing? It says the derivative is that big hairy mess there. That's because this is a simulation and there's random noise and everything in it. So let's dig into that a little bit. I'm going to delete that guy in the background and leave just that there. And this guy, I'm going to say, this is a hard to explain, but basically this is an advanced form of averaging. I'm going to say average it over a certain fixed interval. You'll see what that does in a second. From 55, which is the minimum number there, to 707. These numbers are got from the axis, and it's suggesting 77. That's just some random number. I'll turn it to 73. I don't know. There's no particular reason. Let me make this 99. So what the tool is going to do is it's going to step by 99s through this range and repeat it with the average. Just watch what happens. Right. So now I'm going to delete that guy in the background, and that is the kind of average that we're getting. That is the estimate from this simulation of the noise per square root hertz that we've got as a result of sampling a signal with a 1 picofarad capacitor. Let's see if that lines up with what the web teaches us. The web says to us that the noise will always appear in the Nyquist range. Well, we know what the noise is. It was this thing up here, look. That guy there, let's just bring him down again. That was the noise taken by a capacitor from KT over C. And again, it's about 65.23. So the web teaches us that that noise will appear in the Nyquist range. Let's see if that's true. Let's divide that noise by the square root of the bandwidth that we've got, which is the square root of, this is sampling at 100 megs, so we've got 50 meg bandwidth. So this is now the noise per root hertz in theory. 9.224 nanos. That's pretty close, isn't it? I'm going to add a marker there, and then I'm going to adjust it. That marker, I'm just going to tell it it's informational, and I'm going to put it at 9.224 nanos. Wow, how about that? Now that I understand it, I'm happy. You see, I never trust the stuff I read on the web. I want to see it work. So that was a demonstration. I'm going to have to put that 9.22 back, aren't I? Informational. Make it pink for no good reason. 9.224. And so many things have been proven by this. Number one, a simple understanding of what the circuit is doing, represented by that code, which is just adding a simple random Gaussian distribution to a sine wave, remove the sine wave, analyze the residual noise, it lines up with theory. There you go. So when we have an A to D converter system that is running at 100 megasamples per second with a 1 picofarad capacitor, we may be scared when we calculate the kT over C noise. Oh my goodness, it's 64 microvolts. Wow, that's big. But when we analyze it a bit more, we see that that noise represents 9.22 nanovolts per root hertz. So that's a number that I'm much more accustomed to dealing with, 9.22 nanovolts per root hertz. A 1 kilo ohm capacitor is, a 1 kilo ohm resistor rather, is 4 nanovolts per root hertz. So this 1 picofarad capacitor sampled at 100 megasamples per second is making the noise of approximately, because it's square root, of approximately 4 kilo ohms, which is not too bad. So we can deal with it. Alright, thank you very much for watching. I hope you found that helpful.